So I will share my screen. I hope you can see.
Yes, please. Yeah.
Okay, you can see
Yeah,
it?
looks nice. Yes.
Okay, perfect.
Okay, perfect.
So,
Thank you.
yeah, I will talk today about the ionic motion in perovskite devices, but making a focus on the importance of the synthesis of a high-quality material to have a good characterization and reliable results. So, as you already know, the ionic motion has a lot of effects in perovskite devices. They are related with hysteresis behavior and recombination processes, of course, related to degradation, capacitance at low frequency domain, and so on. So we will see how to analyze all these phenomena, these effects, using the typical cyclovoltammetry. I will use the laser. Cyclovoltammetry and also the impedance spectroscopy. But as I said at the beginning, I will start first talking about the importance of the crystallinity and the quality of the perovskite material itself. So as you know, the perovskite is a coordinative environment. We need to form the lead I6 4- structure to have the octahedral morphology at the end, right? So to do that, we need to use coordinative solvents, of course, to surround the lead atom, and then provide the molecular interchange when we add the organic cation. So in this study, we analyze the coordinative capability of the most usual solvents, including water as well. So analyzing by the UV absorbance spectrum, we demonstrate that the water and DMSO, methyl sulfoxide, has a very similar coordination capability. So we take this in our benefit for the next work, demonstrating that we in fact have a linear relationship between the relative humidity of the ambient and the DMSO-lead ratio in the precursor solution. It means that if the DMSO and water are competing each other to coordinate the lead atom, then it means that when we have a very high humidity ambient outside the glove box, of course, we will need less amount of DMSO in the precursor solution. And contrary, when we have a very low amount of water in the ambient, then we will need to add a bit more of DMSO to be able to coordinate properly the lead atom. As you can see here in the right images, we have the top view and cross-section of the perovskite devices when we add a lower amount of DMSO than we need and higher amount that we need. So as you can see, when there is a defect of a DMSO-lead ratio with a 40% of relative humidity, we will produce fiber-like morphology of the perovskite. Contrary, when we have an excess of DMSO-lead ratio, we will have the solvent occluded into the perovskite morphology, and then it will produce thin balls in our film. But if we have the optimal ratio, then we will have a very high quality perovskite material. As you can see here, there is a real photo of a perovskite film made outside the glove box, in fact, between 30 and 40% of relative humidity, and we reach almost 19% of efficiency. So that means that it is possible to fabricate high quality materials, high quality perovskite devices outside the glove box, just taking into account this effect. So the first take-home message is this one. The water and DMSO have similar coordination capability, and there is a linear relationship between the relative humidity and DMSO-lead ratio. And then, as I said, it's possible to fabricate just balancing these two features. It's possible to have very high quality devices outside the glove box. So taking into account this previous knowledge, we jump into the next target that we have, that was to reduce as much as we can the VOC losses of wide bandgap materials. And to do that, we optimize the film quality of the methylammonium lead bromide. to obtain a very high crystallinity, as you can see, the XRD, very high reproducible, and also very high stable devices. As you can see here in the JV core, the black one corresponds to the fresh device, just using TiO2 and spiral on top. And then the purple one, is the same device, but after 1 year old, stored under ambient conditions, of course, without any encapsulation material. So once we optimize this wide bandgap material, we jump to analyze through the cyclic voltammetry and impedance spectroscopy to analyze the ionic dynamic and the recombinations that are responsible for the VOC losses. So just a brief reminder about the hysteresis that we can have. So we normally have, well, sometimes we have the normal hysteresis, which means we have better performance in the reverse scans, which means from the VOC, from the short circuit. But we can have as well inverted hysteresis, which means the opposite. We will have better performance from the short circuit to the open circuit scan. This feature has been associated with detrimental performance of solar cells, okay? And as well, the hysteresis, the positive or normal hysteresis, has been correlated with positive capacitance in the impedance spectroscopy. And we will see how inverted hysteresis is related with another type of capacitance. Because I mentioned the impedance spectroscopy, I will just make a super brief intro about this technique. It's a small perturbation technique, which means we are perturbating the system with an AC voltage around a steady state point. And we are registering the output AC current over a range of frequencies, okay? So what we obtain is the impedance spectrum that is giving us, ideally, two arcs, two well-defined arcs. The first arcs, normally in the high-frequency domain, is normally associated with bulk processes. And the second arc, which is appearing in the low-frequency domain, is corresponding to process at the interfaces or ionic motions. The maximum of the two arcs is giving us the time constants of the different physical processes that are giving the resistance to this small perturbation that we are provoking to the system. So the information about the impedance that we can get is about recombination processes and also about charge accumulation. So said that, as I said, this is in an ideal world, but the perovskite behaves in a very funny way sometimes. So we can have as well this kind of impedance spectra. This spectra is characterized by this inductive behavior in the 4th quadrant of the impedance spectra, and it is correlated, we will see later on, with a negative capacitance. This feature will be key to analyze the ionic motion. So the time constant this time is described by an extra branch in the equivalent circuit, okay, with an inductive behavior associated with an extra resistance. And this is giving us the next work that we publish. So we still focus on the wide bandgap material, methylammonium lead bromide, and we use just the usual lithium TFSI salt to dope the mesoporous TiO2 material. And just because we have a very quality perovskite film, we were able to improve the VOC in more than 200 millivolts, just with the use of the lithium. We analyzed the photoluminescence response. And as you can see here, in the black color, we have the band-to-band recombination intensity at 545 nanometers, which is the emission peak of the methylammonium lead bromide. The black corresponds to the lithium one, the device with lithium. But if you pay attention to the red one, which is the no lithium device, we have also the band-to-band peak, but much more quench. But then we have a second feature. We have a second peak at 670 nanometers, which in the case of the lithium device, this peak is quenched completely. If we translate this wavelength into the electron volts, then it's clear that we have the difference, the energy between the conduction bands of the TiO2 and the valence band of the perovskite material. It means that lithium is not only reducing the non-radiative recombination because we are improving the VOC, but also is reducing or blocking somehow the radiative interfacial recombination between the TiO2 and the perovskite. But we need to know, of course, why is lithium doing this? And as I said at the beginning, our main tools are the cyclic voltammetry and impedance spectroscopy. So we analyze the same devices with the wide bandgap material. And as you can see here, we have a higher, a stronger inverted hysteresis for the device without lithium. If you remember at the beginning, I mentioned that the inverted hysteresis is associated with detrimental performance of the solar cells. And in fact, this is true here because we have lower performance, lower VOC for the one without lithium. So we have a stronger inverted hysteresis in this case. And then when we jump into the impedance spectroscopy, we see another interesting thing, and is that we also have a stronger negative capacitance in the case of the no lithium device. So it means the lithium, again, is reducing the hysteresis behavior, but when we don't have this lithium, then we have a strong inductive behavior and a negative capacitance with the hysteresis, with inverted hysteresis. But we need to prove, of course, that this is not a question of the wide bandgap formulation. So we need to prove if, in fact, the inverted hysteresis and the negative capacitance are always related. So we fabricate the typical MAPI formulation. And because we know that inverted hysteresis is correlated with bad performance, we expose our devices to a different relative humidity ambience, because we know water is damaging, of course, our perovskites. And as you can see here, when we increase the relative humidity, then we go from positive hysteresis index to a negative hysteresis index, which means we are evolving from normal hysteresis to inverted hysteresis. When we jump into the impedance, if you pay attention to the green and the yellow spectra, which means 45 and 60% of relative humidity, you see that we have here, in these cases, a huge negative capacitance behavior. So it means that inverted hysteresis and negative capacitance are totally correlated. We analyze the time constant to see why is this happening, in which process, which process is they are associates. And when we compare the timings of a very good solar cell, I mean with a high VOC, compared with the ones with lower VOC, meaning the no lithium device, and also the ones with MAPI but exposed to very high humidity ambience, then we have that the longer times are corresponding to the worst performance, meaning that there is a very slow process governing the operation mechanism. Contrary, for the good performance, then we have shorter times. It means that we are having faster processes. And so that the second take-home message is that, yeah, we demonstrate for the first time that inverted hysteresis and negative capacitance are associated always. And both features are linked with very slow processes corresponding to ionic motion. Their presence in solar cells are a sign of a bad performance, of course, and also they can be present in other non-photovoltaic devices, being even beneficial for the operation, which is the case of the memristor. I will mention this at the end of my talk. So, the next work was correlating the two previous ones that I have already mentioned, using, again, the optimized formulation, wide bandgap, and also the similar, I mean, the same selective contacts. Just we try to analyze systematically that if the lithium is doing those benefits, well, what is going on with the next of the alkali metals? So we use sodium and also potassium to analyze the performance. And then we obtain a very high VOC in the case of the sodium, 1.65 volts, just doping the mesoporous TiO2 with the sodium TFSI salt. But we not only have a very high voltage, we also have a trend, a clear trend. we have the lowest VOC for the reference cells, which means with any alkali metals in the TiO2. Then we go for the lithium, the maximum for sodium, and then the potassium, which is a bit of counterintuitive, right? But then we analyze the hysteresis index just to check, and of course, the lowest hysteresis was corresponding to the sodium. The same happened with the PL lifetime. The highest one corresponds to the one with the highest VOC. But we need to know why is this happening. So we analyze, of course, with our second main tool, the impedance spectroscopy. We analyze the 4 different samples at VOC conditions under illumination. And we obtain for all of them 2 well-defined arcs. But if you pay attention to the second arc, which is related with this low-frequency domain that I mentioned is related with the ionic motion, we see that for reference lithium and potassium, we have here this negative capacitance behavior, which I mentioned was detrimental, right, for the performance. But for sodium, we don't have this negative capacitance, which means the sodium is doing something really good at the interface. But not only on the interface. If we pay attention to the first arc that I mentioned is normally correlated with bulk processes, we see that the recombination resistance is higher in the case of the sodium. So it means sodium is somehow slowing down the recombination processes also at the bulk. But still, we really need to know much more. What is this happening? So we perform TOF-SIMS analysis, and we observe that the slope for the different ions is different for the devices containing potassium in green, lithium in blue, and sodium in red. So as you can see here, the slope is different, and it means that the sodium device is reducing the ionic migration towards the interface. We jump into our next experiment just to be sure. We perform the XPS. And if you see here, the lead and the carbon spectra are almost the same for the 4 samples, reference lithium, sodium, and potassium. But if we pay attention to bromide spectra and nitrogen spectra, there are huge differences. In fact, for the bromide, the peaks are shifted to lower binding energies in the case of sodium sample, as you can see here. However, if you pay attention to the nitrogen spectra, the peak position shifts to higher binding energies. And this opposite shift gives us the idea that perhaps a strong chemical interaction is being produced between the methylamine and the sodium TiO2 device. So we look into the literature to be sure that our proposed mechanism was fine. And we find that Suarez et al., they analyze that the binding of the alkali cations with small neutral ligands, like water, ammonia, and so on, acts in a different ways. When the oxygen is the donor atom, the trend of the charge transfer ability goes from lithium, then sodium, and then potassium. However, when the nitrogen or sulfur are the donor atoms, which is the case of methylamine, then the trend goes from sodium, then lithium, then potassium, which is exactly the same trend that we are having in our results. But also, Davide Serati and co-workers, they demonstrate that, in fact, we have in the perovskite material an equilibrium between methylammonium cation, but also protons, and also methylamine. So this gives us the idea that because we have this trend and all the results previously shown, that sodium is interacting with these methylamine compounds and is blocking the migration of the ions towards the interface. This is the effect that the sodium is doing, and that's why it's improving the VOC with such a high voltage. So the third take-home message is that with alkali metals used as additive just in the TiO2 material, we can increase the VOC of perovskite solar cells by reducing the recombination, which is related with the inverted hysteresis and negative capacitance. And how they are doing it? Well, they are modulating the ionic motion in the perovskite material. And with this, we jump into the last work I want to show you, and is that the ions, okay, they are pretty bad for perovskite solar cell performance, but they are very good, in fact, for another non-photovoltaic devices as membristors. Okay, so again, we use methylammonium lead bromide, but this time to perform a very long endurance and high quality, high performance membristor perovskite device. So we fabricate a single crystal film on the top of a PTA contact, and then using just graphite carbon paste. And this high quality material, as you can see here, gave us the opportunity to have a very high performance membristic behavior with a huge stability. Here in the right side, you can see the evolution of the carbon stability performed at the low resistance stage, which means when the membristor is in the on stage, and during the high resistance stage, which means we have the off stage of the membristor. But this stability allow us to, again, use the impedance spectroscopy and this negative capacitance behavior to analyze the, in situ, in fact, the electroformation process of the membristic device. So when we apply the increasing voltage from 0.3 to 4.5 volts, just to switch on the membristor device, we see that at the beginning, at very low voltage, which means we are in the off stage, in the high resistive stage, we have a huge negative capacitance, which means, because we have previously seen, that we have very slow processes taking place in our device. However, when we are increasing the VOC progressively, then this negative capacitance, as you can see here, is reducing a lot. The graph that you can see here in the middle is the DC current extract from the every impedance spectra at the different voltages. And you can see here perfectly that at 4.5 volts, there is the switch on of the membristor, maintaining them to the on stage. So we calculate, as at the beginning, we calculate the time constants corresponding to this process against the voltage applied, and we observe that we have an exponential decrease of the timing, which means that we are going from the very slow processes to a faster one, okay? So the times goes from slow to fast when approaching the on stage in the perovskite membristor. And the last take-home message, I hope I'm in time, is that the negative capacitance give also a valuable information about the perovskite membristor mechanism. And during the electroformation process, this negative capacitance decreases, going from the very slow processes to faster one. And the timings governing these processes are associated with accumulation of ions to the diffusion of the ions. And with that, I will thank a lot of the institutions involved in these works, the University of Stuttgart, of course, ULISH, and of course, my current affiliation, which is in beautiful Seville. And of course, all of you for your kind attention.
Thank you, Clara, for this fantastic talk. Very insightful. You have many questions. I think we can only go for one or no, let's do two at least. So let's ask the most obvious one for the non-experts by Mariam Haidari Ramshe. Sorry for mispronouncing. Is the hysteresis index relevant? And does a zero hysteresis indicate, like index light stability? Or is it really the MPP that you should measure instead?
Well, it depends what you want to know. In fact, of course, the hysteresis index will depend a lot of the scan rate that you are performing your cycle voltammetry. it will change a lot. I mean, there is a very fantastic paper by Alison Walker that they are showing that depends on the architecture. If you have NIP or PIN, the hysteresis index goes from positive to negative, and vice versa when you go from the lowest scan rate to the fastest one. So you have to have this into consideration, okay? And then the MTP tracking is most related to the stability at one steady state. Yeah. So it's different things.
Yeah, different insight. That's an interesting answer. Yeah. Then we have another question by Zhang Bao asking, when you do impedance spectra analysis, sorry to smile, how do you choose the related equivalent circuit?
This is a fantastic question. Yeah, I mean, the point is you have to be, of course, the equivalent circuit is at the end is a mathematical thing, right? But you have to give the physical meaning of the equivalent circuit. Otherwise, it has no sense. You can fit every spectra with the most funniest equivalent circuit that you can imagine. But if it is not giving us the physical meaning of the perovskite or the device operation, then it has no sense. So there is a huge topic open to be able to make a general, I mean, the most general equivalent circuit as possible.
Yeah.
Also, there is very helpful to analyze not only impedance, but also IMPS and IMVS, the other two small perturbation techniques. So it will be very high desirable to perform the three techniques to be sure that the three of them are matching with the equivalent circuit.
Yeah. Yeah. Okay. Thanks. Always the same question, very difficult and very important, actually. So here is another question by Bidisha Nath. So she's thanking you. And then the question about all these alkali metals, does their ionic radii and interaction volume play a role when they migrate into the TiO2?
Yeah, well, I think, of course, this is a very good point. In fact, as I said at the beginning, this is like a counterintuitive, right? But I think the answer is related with this first premise that I show, reported by Suarez et al. I mean, the charge transferability of the alkali metals depends on the donor atoms that you have, in fact. So it will change. And this, yeah, that's why we will not have this intuitive correlation with the ionic ratio.
Yeah. Then maybe like two more short ones. So one by Amir Habibi, who was very active, asking, so ion migration is a bad thing, right? And then what are the innovative strategies and material engineering approaches to effectively manage ion migration within the device architecture and not destroying the device, obviously?
So if I understand right, the question is like which other strategies are being used?
What could you do to sort of minimize the detrimental effect of ion migration? How can you manage it?
Well, I mean, the first thing, and this is the one, like the main take-home message that I want to give, is that you have to have a very high quality perovskite. Otherwise, you will have thousands of defects, both chemicals and morphological defects, and then you will have a huge vacancies and so on that they are going to migrate and they are going to degrade faster your sample. So this is the first point. The other thing is, if you can, like here, if you can chemically interact with the most migrating ions in your material, then of course you will have benefits in the final performance of your device. Self-assembled monolayer, they are proving to have as well a very beneficial effects on this matter.
Okay, and then last but not least, there are so many more to ask, but I don't want to curb the enthusiasm too much. So it's Max Grzesiak asking, thank you for your talk. In your opinion, can strategies like potassium passivation effectively block ion migration and lead to high VOCs? What other strategies could there be? So it's kind of related to the previous question.
Yeah, with other strategies to improve the VOC, well, of course, you have to have a good energy alignment and so on. I mean, you have to be sure that, because the term of passivation, I don't like that much, never, because it is very vague. I think so. You have to know, in fact, which is the exact interaction of your additive, of your potassium or whatever, what you are provoking, in fact, in your device at the interface and at the back, both at the same time. So yeah, I mean, there are plenty of strategies, but of course you have to be a good material. You have to know properly what the additive are going on, are doing in your material, and yes, to be sure that the energy levels are well aligned. Yeah. That's, I think, it's the main.
So thanks once more on behalf of the audience. There are many more questions actually.